Hello and welcome to Unit 4 Work and Energy, presented to you by the IHS Physics Club. You can join us on Remind at PhysIHS. So with that said, let's get started. Okay, so let's begin with work, a very important concept. We're going to see it as F times D, or force times displacement. Now, displacement is basically how far the force makes an object move. How far, not how fast, how slow, but in fact, it's just going to be the distance. And that kind of tells you that if a force makes an object move farther, then it has more of a contribution and therefore greater work on the object. Right? And we're going to see later this is also equal to a change in kinetic energy. All right, so remember, in most cases, F and D are going to be just scalars. You can just multiply them together. But in some corner cases, you have to take into account the fact that the force and distance are both vectors by nature. And work is actually going to be the dot product between force and displacement, or F times D. So we actually have to rewrite this as F times D times cosine theta, because you're taking into account the angle between the two vectors. And the direction of the work, it's going to just depend on which direction, which way the force is actually acting on the object, or which way the displacement is acting. If one of those is going to be negative, then you're going to see a negative work on the object. And how do we know if displacement is negative? Well, essentially, if the object starts moving in the other direction, or it's trying to, or slowing down, it's going in the other direction because of this force, okay, then it's going to be a negative work. The force is going to be creating a negative work on the object. So just keep that in mind, because sometimes when you're writing your equations, you can't forget to leave out the negative signs. Okay, so now let's take a look at energy. So as we've learned in the past, when we're looking at energy, we first have to consider what kind of a system we're actually looking at or analyzing, right? We have two choices. We can define a system to be closed or open. So just remember that in order for it to be a closed system, there has to be no external forces. So essentially, it's in equilibrium. So there's no forces going into the system. If you, for example, on a diagram, draw like a box around the objects that you're saying in your system, right? And then if there are any forces poking out or going into the object, then those are external forces, because you just defined that border to be inside of your system. So if it's pointing outside, that means it's interacting with something else. So that's actually going to be an open system, and that's not good, especially when you're analyzing energy. So try to look at or define a closed system in your analysis. And remember that gravity is only going to be an internal force, because obviously, if we're looking at objects on Earth, there's always going to be a gravity going downwards. So it's only an internal force, meaning it's only going to be in a closed system if you're saying Earth is also part of the same system. Meaning, if you're just looking at two blocks and you're just saying the system from those two blocks, then gravity is actually going to be an external force. So what you're looking at, unless you're in space or not in the gravitational influence of any planet, meaning you're super far away from any big mass, right? To the point where gravity is negligible, then you can say that it's going to be an internal force, because there's not going to be any gravity to begin with. So just remember that here, most systems, if you want to apply energy conservation, as we're going to see in the next slide, you're going to need to make sure that the Earth is also part of the system. So gravity will become an internal force. So now let's take a look at how many types of energy, what they're for, and how to analyze them mathematically. So in the world, there are many different types of energy. You're going to see in here the words kinetic energy, gravitational potential energy, elastic potential energy, and more. And also heat energy. You've probably seen energy converted into other forms. For the purposes of just mechanics and physics in general, we're probably only going to be working with these three forces. So Remember, conservation of energy is only applicable when a system has no external forces, meaning it's a closed system. That's why in the last slide I stressed so much that we need to make sure that the system is closed, or else we can't do any productive analysis on the energies, right? So conservation of mechanical energy is simply this, that the initial energy at the beginning, adding all these different types of energy up, is going to be equal to the final quantity of energy at the very end of whatever happens in the system. So a few formulas to remember is the potential energy is just going to be mgh. Now, this is talking about when you're very close to the Earth. When you're very close to the Earth's surface, like just at most a few kilometers, say, above the surface. If you're talking about something completely different, like you're in space away from a planet, then you would have to use a different type of gravitational potential energy. And that one would be through negative big G, m1, m2 over r. And r is the distance between your object and the center of mass of the planet, the center of the planet, right? So that's something to keep in mind, but it probably won't be very applicable with the problems that we're tackling. So just keep in mind these formulas. And for the MGH, however, we have a height of h, right? How do we define this h? What is it? Well, it turns out in our conservation of mechanical energy formula, we don't need to worry about what h is relative to any. We define our own 0 point. And that's just the point that I call where we're saying the height is 0. So then we can base all our calculations off of how high something is from that one point. That makes it really easy because sometimes when you're looking at a very complicated system, you can choose one convenient height, one convenient 0 point, and that simplifies the problem so much, as we'll see in the problems and examples that you do on your own. Right? You'll see that choosing the 0 point is highly important, and it's going to simplify your calculations by many times. Something else to know, kinetic energy, as we've learned, is 1/2 mv squared, 1/2 times the mass times the velocity squared. And it's important to note that the change in kinetic energy is the work done on an object. If there are no other forces in other special circumstances, if we're just looking at a simple case, then yes, the change in kinetic energy can be attributed to a work on a system, work done by a force done on an object in a system. Alright, so after having watched this review, I would really recommend taking a look at a few practice problems, trying to find some other resources on work and energy, and just familiarizing and making sure you're able to internalize what is really going on when we're talking about conservation of mechanical energy and the work energy theorem, which is how work relates to kinetic energy. So, in all, thank you for watching, and hope to see you for our next unit.